Well, I would like Administrator Golden and the students and teachers who were involved in this project to stand so that we could thank all of you. You know, creating that interest and excitement among young people about science is something that we really appreciate among our teachers, and the more we can do that through events like this and reaching out, I think the more people will feel involved in the continuing challenge of exploration. Today we have two people to lead us through what is happening in our seas and in our skies. Dr. Marcia McNutt is the president of the Monterey Bay Aquarium Research Institute. She and her husband have just come from attending graduation ceremonies for their three daughters, one of whom finished high school, two from junior high school, and I thank them and congratulate all of them and are glad they're with us. For over 20 years, Dr. McNutt has been a leading researcher, lecturer, and author of over 80 articles. She has personally been on 14 ocean expeditions, but her familiarity with water goes far beyond research. While in high school, she was one of the first women to pass the civil service lifeguarding exam in Minneapolis. And when she got to graduate school, she pushed to train with the Navy SEALs off the coast of California and received an A+ in her course on explosives handling. This is not a woman to mess with under any circumstances. You know, I've been told a lot of stories about Dr. McNutt. One concerns how when she was a poor graduate student in the 1970s, she bought a secondhand motorcycle to get around during the gas shortages of that time. And after breaking her right hand, she insisted that the doctor try 3 different splints to find one that allowed her to keep riding. Well, it's that same level of determination that has kept her going ever since. And as she prepares to become the president of the American Geophysical Union, she will be exploring volcanic islands and other spots about which far too is known still. Our other distinguished lecturer is Dr. Neil deGrasse Tyson, who is here with his wife, Dr. Alice May Young. Dr. Tyson is the director of the extraordinary Hayden Planetarium in New York City. I had the pleasure of seeing the new Rose Center just last week and urge everyone to see this extraordinary place and exhibit. At the age of 9, he attended his first planetarium show, and from that point on, he knew that his answer to the question of what do you want to be when you grow up was an astrophysicist. His life had been changed forever. Years later, he still uses the lamp he made in 7th grade to illustrate Saturn and her rings. But his observatory is no longer simply his windowsill and his rooftop. It is the entire universe. He is the author of 5 books and numerous articles for scientists and citizens. He's a frequent television guest, and as the keeper of the keys to a world-renowned planetarium, he's bringing the mysteries of space exploration to explorers of all ages. No wonder his high school classmates at their 20th reunion voted him the alumni with the coolest job. Well, we think both our speakers have very cool jobs, so now I'm pleased to introduce first Dr. Marcia McNutt, and she will be followed by Dr. Tyson. Dr. McNutt.
Thank you so much, Mrs. Clinton, Mr. President, students, esteemed guests, and my co-speaker, Dr. Tyson. It's certainly a pleasure to be able to share with you my thrill of the oceans this afternoon. The deep sea, deep space, both concepts conjure up the promise of adventure and the riches of discovery. But humans were not designed to survive each, at least not without the benefit of substantial life support systems. And this is a shame because the oceans are the largest habitable living space on the planet. Imagine for a moment that we could all live underwater. The oceans are so vast that if we divided them up amongst us, all 6 billion of us on this planet, we would each have an ocean view living room that was a mile long, a mile wide, and a ceiling 800 feet high. Although people don't live in the ocean, it is indeed a living organism. Most people are familiar with the large animals that live in the ocean, such as whales, sharks, and dolphins. But it's astounding to consider how much life is even in the tiniest drop of seawater. That was 10,000 organisms. Those 10,000 organisms are the microscopic forest which makes for a healthy ocean ecosystem. Despite all there is to learn about this vast living ocean, it is really only in the latter part of the 20th century that the deep sea has been open to direct exploration by humans or by their robotic proxies. So what took so long? Why is it so difficult? Well, first of all, crushing pressures. This is your brain in space. This is your brain at the bottom of the ocean. This is this head taken to the bottom of the Challenger Deep. Without some protection, humans can't survive that journey. And machines have to be designed to withstand pressures that are equivalent to being squished in a trash compactor by a weight equivalent to the Statue of Liberty. Second, the oceans are essentially opaque. Now, the light from this flashlight can be seen by everyone in this room. If we were underwater, it would be difficult for even those of you in the front row to see this light. In comparison, light reaches the furthest edges of the cosmos. The fact that light passes so easily through space is the reason why we knew more about the surface of the moon than we did about the bottom of the ocean, even before we had a multi-billion-dollar space program. But the urge to explore is fundamental to the human spirit. These challenges were overcome by advanced technology that finally would allow a visit to the bottom of the ocean to be a round trip, something which most aquanauts insist on. It's amazing to reflect that when I was graduating from college, okay, so maybe that wasn't just yesterday, everyone firmly believed that all life on Earth was based on photosynthesis, the process by which plants use the sun's energy to make new organic matter. Thanks to the newly developed ability to take artificial lights, cameras, and even humans to the bottom of the ocean, we discovered just how wrong we were. In the middle of the ocean, miles deep into perpetual darkness, a continuous network of volcanoes runs uninterrupted throughout all of the world's oceans. As segments of these volcanoes periodically erupt, they fuel the life support system for a food chain that would persist even if our sun were to burn out tomorrow. The process begins with the release of bacteria expelled from the seafloor during a volcanic eruption. For obvious reasons, we call this a snowblower event. The bacteria exit the seafloor in water that's room temperature, despite the fact that the surrounding water is ice cold. Nearby, water 700 degrees Fahrenheit, but not boiling on account of the high pressure. It's black with particles of hydrogen sulfide, forms chimneys of mineral deposits. The bacteria form the basis of a food chain by deriving the energy needed to create organic matter by breaking the bonds between the hydrogen and sulfur in this hydrogen sulfide of the venting volcanic fluids. Scientists had predicted no life would exist at temperatures this high because proteins would not be able to function biologically. Obviously, that view was very wrong. 11 months later, this food's moved up the food chain to feed deep-sea crabs and tube worms. Just 7 months after that, a total of only 18 months after the onset of the first volcanic eruption, the tube worms have reached full maturity. We'll see in a minute a spawning event in which they are releasing the spores, the larvae that will travel through the ocean looking for new volcanic sites to colonize. Sometimes the colony dies out because the volcanoes die out. Other times, the eruption intensifies and leads to, in this case, a tube worm barbecue. There's some evidence now that this sort of environment was the cradle for life on Earth. As a result of these discoveries in the blackness of the deep sea, the range of conditions conducive for life on Earth, and presumably elsewhere in the cosmos, were greatly expanded. The great discoveries of Woods Hole's Alvin created the demand for even more capable, lower-cost, higher-endurance vehicles for accessing the deep sea. The solution? Use technology to send the human brain but not the human body, to the bottom of the ocean. A remotely operated vehicle, or ROV, explores the deep sea while its team of scientists sits comfortably at the surface at the end of joysticks. So you see, kids, there is a job for which video game experience is relevant. Such vehicles can easily be balanced to hover in the midwater, above the seafloor but well below the sea surface, where they discovered an entire new world of fragile, gelatinous organisms that drift perpetually on the ocean currents. This is a region where scientists predicted little life would exist. In fact, even Jules Verne didn't have life here. After all, nets towed from the surface only came up empty, except for mysterious globs of protoplasm. What was that? It was just about 15 years ago that we realized that the abundant life in this part of the ocean would constitute as much as 20% of the planet's entire biomass. The ROVs showed not only what these organisms look like, but provided the capabilities for capturing them to observe their behavior back in the lab. The ROVs also serve as the scientists' eyes and hands in the deep sea, providing the capability to do tabletop experiments. In this view, the ROV is performing an experiment at the pressure and temperature and other conditions at the bottom of the ocean. Here we test the stability of liquid carbon dioxide injected into the ocean a few miles deep. This process has been proposed as a mechanism to curb the release of carbon dioxide into the atmosphere and mitigate its attendant greenhouse effect by disposing of it in the deep sea. But we need to do many more experiments before we'll know whether deep sea disposal of carbon dioxide is environmentally safe. But not all ocean discoveries are courtesy of underwater vehicles. Exploration of space has provided us with a new tool for studying the oceans. Not long after we began sending satellites into orbit to observe outer space, we realized that the satellites could be turned back to give a bird's eye view of the planet. In this time-lapse simulation based on real satellite data, it shows the development and recovery of surface water prevented the normal, cold, nutrient-rich waters from reaching the surface and feeding the plants and animals there. The ensuing La Nina, which is shown here, just the opposite effect happened, and there was extra nutrients for the oceanic ecosystem. The failed fisheries of the 1997-1998 El Nino may just be the harbinger of what is to come as the globe continues to warm in the grip of the greenhouse effect. Thanks to the installation of automated ocean observatories, we can begin to answer the question of what will be the long-term effects from global warming that puts the planet perpetually into a more El Nino-like state. Over the 10-year period that's represented in this graph from Monterey Bay, you can see the seasonal cycles of cooling and warming in the ocean surface waters. You can also see the intensification of the warming at the right hand of the screen and the cooling associated with the 1997-1998 El Nino. But superimposed on that data in the green line is the long-term trend. It shows a perceptible and detectable warming of the ocean. The amount, it's only about 1 degree Fahrenheit, which may not sound like much. But our observatory also has biological and chemical sensors to determine what effect that 1 degree of warming has on the life of the ocean. Here again, you can see now a plot of the primary production, that is the production of new plant life in the ocean. That 1 degree of warming corresponds to a 25% drop in the rate of plant growth in Monterey Bay. It's scary when you recall that climate models currently are predicting that the globe will warm by several degrees over the next century in response to the buildup of greenhouse gases. One way to imagine what the future might be like is to look back into time. The sediments laid down over the eons in the deep sea are Earth's tape recorder. They give us an unparalleled opportunity to find past examples of greenhouse Earth and what effect it had on the life at that time. The ocean drilling ship, drilling in the western North Atlantic, hit pay dirt, recovered a continuous sediment core with an unusually high-resolution record of Earth history at the end of the Paleocene, 55 million years ago. Recorded in that sediment core was the history of a catastrophic release of carbon into Earth's atmosphere, presumably from the sudden release of methane trapped in ices buried beneath the continental margin. Temperatures soared 5 to 7 degrees in the deep sea. 30 to 50% of small animal species in the deep sea went extinct. The Earth took 100,000 years to recover. So you see, not all catastrophic events are caused by asteroid impacts. Some disasters are very homegrown. For the present, at least, the only known habitat for mankind is planet Earth. We must learn from our past. We must protect our future. Thank you. And now my colleague, Neil Tyson, will tell us about the exploration of space.
You know, I feel bad because I didn't bring a shrunken head to show you. But it's true that if you took this up to the space shuttle, rolled down the window and put it outside in space, it would just explode into countless pieces. They would freeze solid and crumble like a potato chip. So really, the surface of the Earth is a nice place to stay. Mr. President, Mrs. Clinton, guests, colleagues of mine from the scientific community, it's now my task to take you from the bottom of the ocean, where we just were, to beyond the stars. As is hinted to, as a city kid, my first night sky was that of the Hayden Planetarium. And when the lights dimmed, thousands of stars came out, and I was certain that it was a hoax, because I had seen the night sky from the Bronx, and it only had 14 stars in it. So there was no question about it. We have some people from the Bronx here. Am I telling the truth here? Yes. Of course, now as a professional, I've used some of the largest, most powerful telescopes in the world, Earth-based and space-based. In fact, dreams can come true, and it's possible to reach beyond the stars, where, in fact, the sky is not the limit. As Marcia noted, yes, the quest to explore and discover is a powerfully human trait, but it extends further than simply asking what's on the other side of the mountain, or even what's at the bottom of the ocean. Civilizations across cultures and across time have all looked up and asked, where did we come from? How did it all begin? How will it all end? And perhaps the most important question of them all, what is our place in this universe? Now, I want to give you a cosmic perspective to ensure that we're all thinking along the same wavelength. Allow me to remind you of how big the universe actually is. Let's take a nice round number like 100 billion, okay? We've seen this number before. It's the occasional net worth of Bill Gates, you know. And also, every few blocks, McDonald's remind us that it sells that many hamburgers. 100 billion, I think, is the last count. Well, let's take those 100 billion hamburgers and lay them end to end. It's an end-to-end story, but it'll go quick. You lay them end to end, you go 13 times around the Earth. And with what's left over, you can stack them and make a pile high enough to reach the moon and then back again. And only then would you have used up your 100 billion hamburgers. By the way, the estimated number of stars in our galaxy is 100 billion. Let's go up a little more. Add 3 zeros, you go to 1 trillion. If you never slept, nor had any conversations with anybody, never went to the bathroom, you could count to 1 trillion in 31,000 years. How about a quadrillion? One of my favorite numbers, one with 15 zeros. Estimated number of sounds and words ever uttered by all human beings who have ever lived, which includes all congressional debates and filibusters, I might add. A quintillion, one followed by 18 zeros. That's the estimated number of grains of sand on the average beach. But not until you get to 1 sextillion, a one with 21 zeros, have you arrived at our latest estimates for the number of stars in the observable universe. Now, what the past 50 years of technology has brought to us is the capacity to see the universe in bands of light not detectable by the human retina. This electromagnetic spectrum, containing visible and invisible light, is in fact not unfamiliar to the person on the street. Tune your eyes to microwaves, and every cell phone would be aglow. So too, of course, would be the police radar gun on the side of the highway. Microwave telescopes see not only the light emitted and absorbed by molecules in space, They also see direct evidence from the Big Bang. What was formerly intense and mostly visible light from the original explosion of the universe has weakened from traveling 13 billion years in our expanding cosmos. And we now see the Big Bang's glow from the lower energy microwave part of the spectrum. Tune your eyes to X-rays, and the X-ray machines at the airports would be aglow through the dangling curtain that your luggage passes through. X-ray telescopes see the most violent phenomenon in the universe, from explosions on the sun to the ejected matter and energy that narrowly escapes being swallowed by black holes in the centers of galaxies and elsewhere. In fact, the freshly launched orbiting Chandra telescope is the X-ray cousin to the Hubble Space Telescope, now in orbit around the Earth. Gamma ray telescopes see flashes of light from across the universe. These are the most energetic explosions known that to this day defy explanation and understanding. In the universe, major advances in our cosmic understanding of objects and phenomena are traceable to the first and sustained use of telescopes in each one of these windows to the universe. And as much as we praise our eyesight, we're in fact practically blind, because the visible spectrum is only a tiny slice of all the light that's out there. And successful theories of the universe require knowledge in every band before we can claim to have any understanding at all of what's going on. What we have are 7 identical regions of the Milky Way galaxy, the plane of the Milky Way, taken in different wavelengths, going from radio waves, microwave, infrared, visible, ultraviolet X-rays and gamma rays. No 2 of those look alike. And just think, before 50 years ago, the middle picture was all we knew of our galaxy, was all we knew of our universe. Now, unfortunately, Earth's atmosphere is not transparent to all bands of light. It's transparent to visible light, of course. You want proof? We wouldn't otherwise see the sun in the daytime, although this view is made a little fuzzy through turbulence in Earth's atmosphere. But only in the era of the space program did we have the capacity to launch telescopes into orbit above Earth's atmosphere. Half the bands of the electromagnetic spectrum come to us entirely from orbit. But the space program has also enabled us to put robots in space. Robots that have toured and landed on the planets, and on the moons, and on the asteroids of the solar system, which in fact has turned the solar system into an experimental laboratory, formerly only accessible to us from the back end of a telescope. Robots are relatively cheap, and of course we all know they don't have to be fed or brought back from space. We're now in an era where any real scientific experiment conducted by a human is actually conducted by a human carrying a box that performs the experiment itself. So if we send just the box, but enable it to be remote controlled, we have in effect sent up a semi-intelligent robot. Robots are the most affordable way to explore the solar system in detail. But there are trade-offs, of course. While nobody has ever mourned the loss of a robot, I don't remember anyone ever giving a ticker tape parade to one either. The most famous robot in recent memory, of course, came out of Pathfinder, our mission to Mars. You may remember Pathfinder hatched a 6-wheeling, remote-controlled, semi-intelligent scientific laboratory called Sojourner. The Jet Propulsion Laboratory's website that tracked its every move received nearly 1 billion hits, all for a cool hunk of metal the size of a microwave oven. Here it is investigating one of the largest rocks near the landing site. Astrophysics and the earth sciences are probably the most philosophically alike among the scientific disciplines. We're both primarily observationally based, and also just as Earth's history is laid bare in the fossil records and in the accumulating signatures of geologic activity, so too is cosmic history recorded. Telescopes serve as time machines because it takes light time to reach us from everywhere in the universe. From your face to my eye, it takes about 20 nanoseconds. 20 billionths of a second. Light from the moon crosses the nearly 250,000 of miles of space that separate us, which then left the phone call between President Nixon and the Apollo 11 astronauts requiring a round-trip time of about 3 seconds. The nearest large galaxy, the Andromeda Galaxy, we see not as it is, but as it once was, 2.5 million years ago. So they'll just be learning about this event in about 2.5 million years. Long thought to be a closed system, we now know that Earth has been slammed in the past by asteroids and comets, wreaking global, climactic, and biological catastrophe. If that happens again, when it happens again, that would be bad. We can't photograph this because you'd want to be doing other things if it happened. So the best we can do is get space artists to depict this. Noted space artist Dan Davis captured some of this terror in his depiction of an asteroid hitting Earth's oceans. Apologies to Marcia, it's hitting the oceans here. In fact, it's actually not all that bad, because such impacts can also deliver organic molecules and water to Earth's surface. And by having knocked out the dinosaurs 65 million years ago, they enabled mammals to evolve into something more ambitious than a tree shrew. We also know that meteors can hop from one planet to another. Recent calculations show that a major impact can eject surface rocks into space, escaping the planet's gravitational embrace. Indeed, some meteorites on Earth have come from the moon and from Mars. But that gets you thinking. Mars was once a pretty wet place. It may have once harbored life. If bacterial life stowed away on one of those rocks, then life on Earth may have been spawned by life from Mars. So yes, we all may be Martian descendants. In spite of the record of mass extinctions brought by random impacts, life in the bottom of the oceans has remained relatively unperturbed. There's much to learn from this life because it's life that requires no sunlight. Perhaps life on the ocean floor can serve as a model for what life might be like on Jupiter's moon, Europa, which is kept warm not by sunlight, but from the stress caused by the action of Jupiter's gravity. Here we have Jupiter and its 4 Galilean moons, named after Galileo the man. And a detailed close-up from the surface of Europa, which would be impossible without deep space probes, showed signs of fractured ice sheets afloat on top of what is almost certainly an ocean of water. How different could the chemistry of life be elsewhere? We don't know for sure, but the ingredients of life as we know it match almost one for one the ingredients in the universe. For me, the most profound fact of my life. Go right on down the list. Hydrogen, oxygen, carbon, nitrogen, right on down to iron. They're also the most common ingredients in the universe. These heavy elements are traceable to the exploded remains of one or more massive stars that forged these elements in the core by the action of thermonuclear fusion. These stars then blew themselves to smithereens, giving their lives to enrich the galaxy with the manufactured heavy elements from their core, enabling planets and people to form. Here we have a view of a supernova remnant in the constellation Vela, one of my favorite images of the cosmos. This ejected material will enrich gas clouds that will make solar systems. Yes, we are stardust. In space, 2 siblings flank Earth. Venus, closer to the sun, has a thick, seething atmosphere checking in at 900 degrees Fahrenheit, which is not only hot enough to melt lead, but more important, it's hot enough to cook a large pepperoni pizza in 9 seconds. The Venusian atmosphere is hostile, nearly 100 times the pressure of Earth's atmosphere. It's made primarily of carbon dioxide, upon which we can blame its runaway greenhouse effect. Mars was probably once a paradise, an oasis of running water, with an atmosphere dense enough to support it. No longer, it is bone dry. Only relic riverbeds and floodplains and silent river deltas remain. Yes, bad things happen to good planets. Mars and Venus may be the endpoints of climactic evolution gone awry. How do we prevent our cherished world from becoming another casualty in the solar system? By combining cosmic discovery with the earth sciences, our insights may offer us more than just fulfillment of our idle curiosities. Our insights may enable us to save ourselves and to perhaps get to know our planet for the very first time. Thank you.
I have 100 questions. Before I open the floor to questions, I just would like to make a couple of points. First, I want to thank Dr. Tyson and Dr. McNutt for truly fulfilling the spirit of this wonderful old room. It was in this room, on this floor, with maps and books on animal skins that Thomas Jefferson and Meriwether Lewis planned the Lewis and Clark expedition. They were exploring the far reaches of North America, looking for an ocean no one believed at that time you could reach by land. Today, our speakers have taken us on a very different journey of discovery. They have shown us that new evidence is emerging from both the seas and space about so many things, but as you have heard, among other things, about the challenge of global climate change. Just this morning, some of our leading scientists released a draft report that provides some of the most detailed information yet about the potential impacts of global warming on our nation. Some of its findings, because it's a draft, may be revised, but essentially this report pulls together an enormous amount of scientific analysis, and as our previous speakers have done, it paints quite a sobering picture of the future. It suggests that changes in climate could mean more extreme weather, more floods, more droughts, disrupted water supplies, loss of species, dangerously rising sea levels. Now, I have tried for several years to get the United States to respond, to do our part. We are the largest emitter of greenhouse gases in the world. In the next couple of decades, China and India will surpass us unless we all take advantage of the fundamental changes in the nature of the economy to prove that we can have economic growth and reduce greenhouse gas emissions. So it is, if you will forgive me, I want to make one earthly plea, which is that the Congress stop blocking our common sense efforts to combat global warming. We need a climate change on Capitol Hill on this issue. And it should not be a partisan issue. This is about science. This is about evidence. This is about things that are bigger than all of us, and very much about our obligation to these children here to give them a future on this planet. We are not yet prepared to live under the sea, as we have just been told. I'd also like to make one other announcement about ocean exploration. In spite of all that we learn today and all that is known, more than 95% of the underwater world remains unknown and unseen. And what remains to be explored could hold clues to the origins of life on Earth, to links to our maritime history, to cures for diseases. The blood of a horseshoe crab, for example, provides a vital antibacterial agent. A potential anti-cancer drug may come from a deep-sea sponge. 2 years ago today, we held the first National Oceans Conference in Monterey to bring experts together to chart a common agenda for the 21st century. Among the key recommendations that grew out of that conference was the need to establish a national ocean exploration strategy. One of the success stories that has come out so far occurred half a world away on the Navy vessel, the Trieste, which you saw in the video. In 1960, the Trieste went to an area called the Challenger Deep in the Pacific, the deepest spot in any ocean, nearly 7 miles down. Only 2 people have been there. One of those brave explorers was a young officer named Don Walsh. President Eisenhower gave him the Legion of Merit here in the White House more than 40 years ago. He's here today, and I'd like to ask him to stand up. Mr. Walsh. You might say, looks fit enough to make the journey again. I'd also like to recognize the man who discovered the wreckage of the Titanic, who's here, Dr. Bob Ballard. Would you stand up? I want to announce some new steps we're taking. First, 3 new first-of-their-kind expeditions off the Atlantic, Pacific, and Gulf Coast. Voyages led by the National Oceanic and Atmospheric Administration in partnership with major research institutions. These expeditions will allow the first detailed exploration of the Hudson Canyon off New York. It's an underwater version of the Grand Canyon, only larger. The middle grounds and Big Bend areas off Florida, which include some of the oldest life forms on Earth, giant tube worms, you saw some on the film, up to 250 years old. And the Davidson Seamount, an inactive ocean floor volcano off Monterey. In each expedition, researchers will use cutting-edge deep-sea diving technologies and share their discoveries with schools and the public through the internet. Second, to ensure that these voyages are the start of a new era of ocean exploration, I'm directing the Secretary of Commerce to assemble a panel of leading ocean explorers, educators, and scientists to develop recommendations for a national ocean exploration strategy and to report back to me in 120 days. These steps could bring about, quite literally, a sea change in our understanding of the oceans. We must continue as a nation to set out for new frontiers, whether under the sea or into the heavens. We must continue to try to conquer the seemingly impossible, to discover the unimaginable, to find out more about what's out there, and in the process, about ourselves and what's here. I would like to ask the first question, and then we'll turn it over to the regular process and the many thousands of questions that must be out there in this room and beyond here. I'd like to ask Dr. McNutt and Dr. Tyson what they think the most likely discovery in the next 10 years in their field is that would have a significant impact on how we live on Earth, or what our understanding of our system is. Thank you. You go.
Well, as has been said before, it's very difficult to say much about what hasn't been discovered yet. But I think just looking at the great advances that we've already had from recent discoveries, for example, the thermophiles, which are these creatures which love to live in the warm water. They have organic molecules that function at very high temperatures, and those have been used in industrial processes because of their resistance to breakdown at high temperature. The other recent examples are some of the new drugs that have come from the exotic sponges found in the deep sea. If I could say in the next 10 years what will be the most important thing we'll find out about the oceans is hopefully we'll learn to preserve the oceans and that ecosystem. The large majority of inhabitants on this planet depend on the oceans for their protein. Right now, we're starting at the top of the food chain and fishing the oceans to depletion. I think one of the most important things we can do in the next 10 years is figure out how to reverse that process, how to stimulate production in the oceans rather than cut it, and to keep the oceans healthy and productive, not only for our food system, but also for our climate system.
If I could just emphasize one thing. The point you just made is related not only to pollution, traditional pollution of the oceans, and overfishing, but also to climate change. When I was in Monterey Bay, I saw small creatures right in the bay that just 20 years ago were 20 miles south. They had made their way 20 miles in 20 years, these minuscule creatures, because before that it was too cold in Monterey for the creatures to exist. This is real, and we have got to, I hate to keep beating on this, but remember what the kids used to say several years ago, that denial is not just a river in Egypt. That's what we have got to come to grips with this. And you were terrific what you said about it in your presentation. Thank you.
Yeah, I think it's really just a matter of money. And then
Good for you.
I want to go digging under the surface of Mars and see if there is fossil evidence for a once thriving biota. Just dig in the floodplains where we know there was once liquid water. I want to go ice fishing through the thick ice of Jupiter's moon Europa, see what's down there. It's an ocean. We have pretty good evidence that life began in our own oceans. We've got an ocean there, rendered liquid the entire life of that moon. I don't know if that can happen within the next 10 years, but it's not out of our reach as a nation that has sustained a space program for this long. I can tell you that the knowledge of what is there under the ice of Europa and below the surface of Mars, if there's any evidence, confirmable evidence that there was once life there or that there's life there now, that would signal a change in the human condition that we might not even be able to imagine, realizing that we are not alone in the universe. So often the stereotype of extraterrestrials is some intelligent being walking up and down in a flying saucer, but in fact it's no less exciting to find microorganisms there, realizing that it's an entire biology distinct from Earth. That could happen in the next 10 years, if not certainly in our lifetimes, and that would just be tremendous. But in addition, we're now discovering things about the large-scale structure of the universe that only a few years ago were just theories. And the behavior of the universe, from its earliest times to its distant future, tells us what our home, you think of Earth as our home, but I think of the universe as our home. And I'd like to know, what's the shape of our home? What's in our backyard? What's in our front yard? And if your sense of what is home is broadened to include the entire universe, then to discover that we live in an accelerating universe, or maybe the universe has structure that enables you to look one way and see the back of your head in the other direction. These kinds of discoveries enable you, upon coming home at night, to think about something different over dinner after you worked your job from 9 to 5. And this enriches our culture. This is the culture we will pass to the next generations, what we have discovered about this universe. And these are right now within reach. And they come to us through space probes and through the construction of our largest telescopes.
And Ryan Wagner, who's an 11th grader from Grafton High School, Newport News, has a perfect follow-up question to that.
Okay, thanks.
How might deep sea space exploration increase environmental conservation efforts in the future?
Should I start with deep sea? All right. We can't preserve what we don't know about, and we can't love what we don't know about. So I think by the images that the deep sea brings back and by the specimens that are shown in the aquariums, that is how we understand what is there and what needs to be preserved. And without that exploration, people might view the ocean as an infinite dumping ground that can take all our nuclear waste and all our trash. But once we find out what those creatures are like that live at the bottom of the ocean, we understand how important it is to preserve them, because we also understand what role they play in the overall global cycles of energy, carbon, and everything else which makes Earth a habitable planet.
You know, we don't know what all the knobs are that control what goes on Earth's surface and Earth's oceans. Some of those knobs might reveal themselves to us by studying our nearby planets, Mars and Venus. As I said in my presentation, these are perfectly good planets gone bad. I want to know what made those planets go bad. There might be some knob that was turned that we can prevent ourselves from turning on our own ecosystem. And so when I think of how space exploration can enable, can promote the survival of our own species and our own biota, I think of our neighboring planets and ask, what can we learn from them?
Mrs. Clinton, shall we go to the internet?
This is a question from Eric Gondry in Minneapolis, and it's for the president. President Kennedy's challenge in the early 1960s to land a man on the moon gave a major push to space exploration technology and our understanding of the universe. In our time of prosperity and rapid technological advancement, no similar national priority exists for a manned Mars mission. Do you feel that a present-day challenge delivered in the spirit of President Kennedy to send a manned mission to Mars before the year 2030 would be an appropriate priority for the new millennium? I think Eric is probably Dan Golden's nephew.
Well, let me say, I think one of the interesting things to me was about the previous discussion were the comments that were made by both our speakers about the importance of robotic exploration of the deep sea and outer space, and about what could be done now with the technology. So I would leave the question of that first to this space program. But if Dan Golden told me that we needed to send a man to Mars to find out what we need to know, then I would strongly support it, because I think the United States would make a terrible mistake to weaken either its space exploration or its undersea exploration. I think we should accelerate it. I think we should invest more money in it. And I think we should keep pushing the frontiers of knowledge. We just went through a very wrenching period where NASA had to basically learn to do more with less. We were trying to get rid of this terrible deficit. Now we've got a surplus. We're paying down our national debt. We're investing in our future. And I think a big part of that investment ought to be the broadest possible commitment to science and technology, including vigorous exploration of outer space and the depths of the ocean. That's what I believe, and I hope that will be a commitment the American people will extract from their candidates in this election season and in everyone for the foreseeable future, because it's very, very important.
I'd like to recognize another explorer. Dr. Sylvia Earle led the first team of aquanauts when Apollo 13 was in the sky. Now she's explorer in residence at the National Geographic Society and director of the Sustainable Seas Expeditions. Dr. Earle.
I have a question for Dr. Marcia McNutt, if I may. You pointed out that we have had made revolutionary discoveries in the past century, and especially in the last 25 years, and yet with all of our new technologies, most of the ocean remains unknown, unexplored. And you've also pointed out that it's difficult to care or to know what to do about places that you know so little about. So in the 20th century, we saw a great commitment to going skyward with technologies that stretched us in that direction. I'd like to know what you think, what the possibilities may be for the 21st century in the other direction, with special reference to the use of manned and woman submersibles, as well as your beloved robotic techniques.
Okay, well, thank you, Dr. Earle. As a very famous ocean explorer once said, we have made the investment needed to venture into the skies, and it has paid off mightily. We've neglected the oceans, and it's cost us dearly. I believe those were your words. It is... There's still so much about the oceans that we don't know that will require a program that involves both robotic technology and manned technology. As I think Dr. Tyson made the point, we not only need the technology that can take an entire classroom to the bottom of the ocean at once and let them all feel part of the experience, and of course Dr. Ballard has been a pioneer in taking classrooms to the bottom of the ocean, but we also need the heroes that can go down and experience firsthand, come back and tell us all about it, and Don Walsh is certainly a shining example of that. Unfortunately, with the present level of our budget, we have a hard time sustaining much in the way of either a robotic program or a manned program, much less trying to do both simultaneously. It's hard, of course, to compare budgets, but my estimate is that the ocean budget currently is about 1/10 of the space budget. It's an order of magnitude less. And I would love it if we could, within the next decade, ramp up the oceans budget to be at least comparable to the space budget, and I think then we would have a terrific program that could start breaking down some of those barriers to the understanding of the ocean, the discovery, and understanding how the system works.
If I could just say one word to complement that. My science advisor, Dr. Neil Lane, is here. We have tried very hard to increase the entire budget for science and technology. and especially the research budgets. And basically what happens is we get in this debate with Congress. They're more than happy to invest more money in the National Institutes of Health, and that's good. We all want to live forever, even though we're not. But there is one of the things that I think needs to be addressed, and we're trying to write it a little here in this last budget process I'll be a part of, but I've been fighting this for 3 years now. It's a terrible mistake to think that the only kind of scientific research we need to be healthy on this planet is in biomedical research. It's very important, but to have just that and to neglect what we should be doing in space, what we should be doing in the oceans, what we should be doing with nanotechnology, what we should be doing with a whole range of other technology-related issues, all of which in the end have to be developed if we're going to know as much as we can about how to live as long and well as we'd like to on this earth. It's a huge debate. So if any of you can make any contribution to writing that balance, I, for one, would be very grateful. It's a major, major intellectual challenge that we face in the congressional debate. Again, I say this should not be a partisan issue. This is a question of what is the right way to do the most for our people in the new century.
Well, I think this might be a good time for a special message from under the ocean.
President, Mrs. Clinton, esteemed scientists and students from the tropical seas and coral reefs of NOAA's Florida Keys National Marine Sanctuary. It's clear that I'm not actually out on the reef, but instead my greetings come from inside the world's only underwater laboratory, Aquarius, located 3.5 miles offshore of Key Largo, 60 feet underwater, next to deep coral reefs. Aquarius is sometimes referred to as our nation's inner space station, where aquanauts explore and study the underwater realm during missions that last 10 days. You might wonder what it's like to live and work underwater. Well, quarters are tight but comfortable and efficient, like a motorhome. Everyone has their own bunk with a really spectacular view of the reef. A small refrigerator and microwave are used to supplement mostly freeze-dried cuisine, and it's not that bad. There's also space for computers and sophisticated lab equipment. The real story about Aquarius, however, is outside, and outside means the coral reef. Aquarius aquanauts escape the limitations of conventional scuba diving through the use of a special technique called saturation diving. This avoids the serious diving disease called the bends and provides nearly unlimited bottom time to study the reef. The laboratory itself is 43 feet long and weighs nearly 180 tons. Research projects supported by Aquarius contribute to a growing body of knowledge about factors affecting the condition of economically important but endangered coral reefs in Florida. For example, water quality studies are evaluating sources of pollution, and because Aquarius is located in a marine protected area, data collected over the last 10 years provides a foundation for scientists and managers to better understand and conserve this critically important ocean resource. Support for Aquarius comes from NOAA to the University of North Carolina at Wilmington, which operates Aquarius. This partnership is responsible for the longest running and most productive underwater lab program ever. We'd like to thank NOAA and Dr. Baker for their support. You can learn more about our program at our website, where we have underwater web cameras, expedition journals, and lots of project information. So long from Aquarius, and see you underwater.
We have a question from Roxanne Nicholas from Manassas, Virginia, and it's for Dr. Tyson. Dr. Tyson, can you see the Big Bang?
Cool question. Yeah, it depends on what you mean by see. If you broaden the notion of see to finding evidence that supports it, the answer is yes. We see back to several 100,000 years right after the Big Bang using visible light, using light from the electromagnetic spectrum, and that's this microwave evidence that I described earlier. Because before that in time, the universe was opaque to the transmission of light. But there were things that happened before then. For example, there's a period where neutrinos were released, this ephemeral particle that's very hard to detect. If we whipped out a neutrino telescope that had very high sensitivity, you could see farther back in time to the first few moments of that explosion. If we perfect our gravity wave detectors, you can see even farther back to gravitational episodes at the very first few moments. And so, like I said, as you look farther out in space, you are looking farther back in time. And at a 13, 15 billion-year-old universe, if you see that many light years away, you are seeing the evidence of the Big Bang. So the answer is yes, and it continues to be supported by data, much to our amazement and joy, actually. It's one of the triumphs of our models of the universe. When you think, for centuries, people have tried to wonder how we got here and what the origin of the universe was, and it was only in the last several dozen years that we've had scientific data to answer those questions, to be something more than just mythology.
Well, let's go to Dr. Warren Washington. He's senior scientist at the National Center of Atmospheric Research in Boulder, Colorado.
I have a question to both of you, and that has to do with how does studying life at the bottom of the ocean really tell us about the possibility of life either on Mars or on the moons of Jupiter?
Well, one thing we learned from studying life at the bottom of the oceans is that it is possible to have life with two ingredients, water and volcanoes. That's it. So that means that if we look around the solar system, we can find places that might have water and might have volcanoes, and that might be enough to produce life. Certainly before we started studying life at the bottom of the oceans, we would have said, oh, we need a temperature range that's right around 20 degrees centigrade or around, 40 to 80 degrees Fahrenheit. We need sunlight. We need all sorts of things. Now we found that there are much broader conditions under which life can exist, and that has greatly expanded the possibility of finding life in areas that we otherwise would have thought quite hostile.
Yeah, we spent decades thinking about the habitable zone around stars. If you go a little too close to the star, your water evaporates. A little too far away, it freezes. And we know that life, as we know it, requires liquid water, and that was our paradigm. And with the discovery of life under the oceans, that has basically shattered those restrictions on how we can think about the ecosystems that can support a biota. And so we're especially fascinated by how this life survives, how it regenerates, how it came to be. It may be, for example, that after the next meteor impact and 90% of the surface land species are extinct, that we rely upon the life at the bottom of the ocean to jumpstart life back on Earth. So it's taken us places that we hadn't ever thought of before. And this is a true hallmark of frontier science, about which we're all quite excited.
Well, let's go to another student. Tiara Sumter. Where's Tiara? Tiara, hi. Tiara's from a sixth grader from River Terrace Elementary School.
My question is, who owns the ocean? Nations, individuals, or no one?
Okay, very good question. Well, I'd have to say probably the fish on the ocean. But since you give me a limited number of choices here, near the coastlines of various countries, nations lay claim to them. Most of the open ocean is considered international. And that brings with it certain advantage, but also certain problems. Some of you may have heard of something called the tragedy of the commons, when land used to be allowed for open grazing by just anyone who wanted to put their cows out there. Well, what happened was too many cows were put out there, and all the grass was eaten, and the land was no longer able to support any cows. Well, this is the problem with the oceans, because no one really owns it. It's very hard to regulate who takes the wealth from the oceans, the fish, the minerals at the bottom of the ocean, all of the other bounty of it. I think that we would have a much easier time trying to enact what we need to enact in order to preserve the oceans if someone actually were responsible for it. And right now it's very difficult for us to prevent people from over-exploiting it. So it's a good question, because since it's international, we all own it, but no one's really able to take responsibility for its proper stewardship unless everyone agrees to do that.
But isn't that also part of the problem in translating into public opinion and policy decisions the concerns about the environment? I mean, people are still not as aware of a lot of the issues that you've raised with respect to the oceans, you could add the rivers, the streams, the lakes, the air. From both of your perspectives as scientists, what are the best ways that you think we can raise that public awareness and create the conditions for change to protect the oceans and to, better protect life on Earth? Because right now there doesn't seem to be a lot of understanding or support for the changes that probably you believe should be undertaken.
Well, I have to say, Mrs. Clinton, I think you're doing the right thing by inviting these school children here. These are the people we have to start with. And they will take home the message from here today, and they will talk to their friends about it. They will talk to their parents about it. They will become voters. That's what we need.
Well, back to the planets. Dr. Chris Chiba, you're a planetary scientist, co-director of the Center for International Security and Cooperation at Stanford University, and you also hold this Carl Sagan Chair at the SETI Institute.
I would like to ask the two speakers to look ahead 10 or 20 years and speculate on the role of information technology and the internet in your fields. In planetary science, for example, I think we can foresee that over the next decade we will put into place a kind of telecommunications network at Mars. So the internet will become interplanetary, and the students here and all of us will be able to turn on our computers in the morning and see continual live video from a rover on Mars or from a balloon floating in the Martian atmosphere. And I think that will have a powerful psychological effect, inexorably making us think of ourselves as a species that spans the solar system. And I'd like to know if you foresee similarly powerful impacts of the internet or information technology in your own fields.
Yeah, that's an important aspect. First, if we recognize that science proceeds at an exponential growth rate, and part of what stokes that exponential growth is the sharing of knowledge and information efficiently and swiftly. And the internet has certainly led that effort, especially with the growth of computing power as well. I would say that if we have sort of the Mars channel, if you will, where you tune into the Martian landscape at will, I think, yes, no question about it. If that's one of the things that you channel surf through to get to your next sitcom, you might pause there and think about what's out there. And it could introduce a change in how you think about your life on Earth. Because here's this other fragile world out there, a world that is no longer so distant because we've landed there, we've snooped around, and now you have a daily view of it in your living room. I think the internet will transform, as it already has, it will continue to transform space exploration and make the solar system, the galaxy, and the universe, as I said a moment ago, the extension of what we think of as home and what is in our backyards. And this aspect of it I see continuing beyond. You put one of these on the moon, on Europa, and then we can eavesdrop on all that goes on in space exploration. And I don't see why this couldn't also happen in the bottom of the ocean.
We have exactly the same vision for the bottom of the ocean. Networks of observatories on the sea floor and all the way up through the water column to the sea surface, which can send their information either relayed through satellites or through cables to shore that would go to every classroom. And we might ask different schools in the nation to be in charge of monitoring certain sections of the ocean, to look for certain environmental problems that might be propagating through the system, to make every high school part of the stewardship of the oceans. I think it's something that there's certainly no fairy tale in terms of the technology we'd need to take that on. It's simply getting the national dedication to do it.
And right now we're on the cusp of establishing a national virtual observatory with a repository of all the astronomical data of objects in the universe. You can sit at your computer, type in a coordinate on the sky, and in would come the summation of all the world's data, enabling you to look at the universe from your desktop. And I think this is in our future, especially with the handling of massive data sets.
Speaking of the internet, we have another question.
Well, actually, this question follows very closely from what Dr. McNutt just said. It's from Patrick in Canton, Michigan. How much of the seabed has been mapped out, and is it feasible to construct large deep-sea research labs on the seafloor, large enough to provide a comfortable living quarters as well as research areas?
Okay, well, let me take the second question first. I think we just saw a broadcast from one of those deep sea laboratories that provides both opportunity for doing research and for living underwater. And certainly there are no barriers to doing more research labs just of that sort that would allow humans to directly experiment in the deep sea. In terms of how much of the seabed has been mapped, as the President explained, it's actually a very small part of the ocean that we've either directly observed or been able to map with ships using sonar systems. However, quite inadvertently, we got what is a fairly good resolution map of the seafloor, and that was when the CSAT satellite was launched. It had a radar altimeter on it that would measure the height of the ocean, and the purpose of this satellite was to actually determine ocean currents. But some very clever scientists figured out that because the ocean's surface follows the Earth's equipotential, that all the little bumps and wiggles in it corresponded to topographic features on the floor of the ocean, and they figured out how to invert that data to get a picture of the map of the bottom of the ocean. So right now, the best picture we have of the shape of our planet comes indirectly from measuring the sea surface itself, not from actually mapping the bottom of the ocean, which just shows sort of a happy circumstance that wasn't intended that way.
And from space.
From space.
Well, we said they were linked. Now, for another way of looking at exploration, I want to call on our chairman of the National Endowment for the Humanities, Dr. Bill Ferris.
For thousands of years, our artists and writers have anticipated the work that you're doing, from the myths of Aeschylus and Daedalus and Icarus learning to fly, to Captain Nemo, 20,000 Leagues Under the Sea. Do these voices speak to you in the work that you do, and if so, how?
What they do for me, let me broaden that question to include even first-run films that tap the adventure in us all in one way or another, taking you through the lens of the science fiction writer into the future. I think that's extremely important to keep people forward thinking. You point to a few writers who were more successful than others about what has ultimately come true in the modern world. The fact is, regardless of what comes true, when you read these books and you see these stories, they're adventures into the unknown, taking a little of what you do know and extrapolating it into the future. They help stoke sort of our soul of curiosity, and they help promote how you might act when confronted with the next bit of legislation about what the future will bring, what the funding would bring to some. For example, I remember this, just a quick story, seeing Star Trek in the 1960s. And they had this little card about this big, and they'd pop it into a computer, and out would come some data. And I said, oh, that'll never happen. You know, that's the computer disk, and now we're even well past that. And I just keep thinking of how important this is to keep us all dreaming. Because without these dreams, life just freezes up and leaves us cold.
I think the only thing I'd add to that is, in every case, the truth has been more exciting, more fantastic, and more thrilling than even the best science fiction writers. And I think that's the message we all have to remember, is that, that there's even more out there.
Well, I think we have time for one more question.
This is a good one from Susan Roberts here in Washington for Dr. McNutt. In your talk, you mentioned that there is no light and hence no photosynthesis at the hydrothermal vents. What is the source of energy or food for all of those animals?
Okay, that's a very good question. The photosynthetic community uses energy from photons, from light, in order to take carbon and carbon dioxide and to make new organic molecules, for which carbon is the basis. In the deep sea, the bacteria take the hydrogen sulfide, which comes out of the volcanic events, and it breaks the chemical bond in the hydrogen and sulfide, and when it breaks that bond, it uses that energy to fix carbon into new organic matter. So it is entirely independent of photosynthesis in terms of that energy source.
Well, Well, these internet questions keep coming, so let's...
Well, here's another one. This
more.
is from the team at Challenger Center for Space Science Education in Alexandria, in Virginia, for Dr. Tyson. And for Dr. McNutt. From your perspectives as scientists, what are the key characteristics young people today should focus on to participate in the explorations of tomorrow?
I'm really opinionated about that.
Good.
You know, I go to schools and kids say, oh, I don't like math, or I don't, you know, I should be talking to you. They say, oh, well, you all are grown up already. It's too late to help you. I don't like math, and I think to myself, well, you know, math looks kind of exotic because it uses funny symbols and things, but so do other languages look funny. Look at Russian, you look at Chinese, you look at Japanese. If you just looked at a book on Chinese, you don't say, oh, it's too hard. You'll say, oh, I just don't happen to know Chinese. Maybe if I study it, then I'll get to read the book. So science and math, it's just a pathway to being able to speak the language that enables us to describe this universe. That's all it is. That's all it is. And so in my life, yes, I took a lot of math courses, a lot of science courses, because it excited me, because it in fact was empowering. It enabled me to look up and say, no, that's not just this otherworldly place. I understand how those planets move. I understand how those stars make energy. And I know how the universe is evolving. So when I walk out and see my 14 stars from the Bronx, I feel fully empowered. And I think this is important through your schooling, because it enables you to overcome what might be hurdles that come up that you might have thought were insurmountable. But the fact is, if you master the math, master the science, there's nothing in your way. Nothing. And we need you. Badly.
I think the only thing I'd add to that is never stop asking questions. If your teachers tell you the way things are, you ask them why. When they tell you why, you ask them how. And if you come up with a different way to do it, you ask your teachers why not.
And also, as parents, people often ask me, well, how do I make sure my kids go into science? You know, the one thing they should do? Get out of the way. Because kids are born asking questions. It's when you say, oh, you know, shut up, sit down, don't bother me. That's when you start squashing that element of curiosity. And the answer is not as important as the question in any of this.
I think we can do one more.
From Kirsten Armstrong from Arlington, Virginia, for Dr. Tyson. You know, this is along the lines of what we've been talking about. Are we coming closer to finding planets like our own? Now, you've mentioned Europa, you mentioned Venus and Mars. What else might be out there? How much further might we go?
Planets are coming in fast and furious. Just a couple of weeks ago, 8 more were discovered, planets outside of our solar system. I've lost count from this morning, but we're over 4. We're rising through 40. 40 planets not within our solar system discovered in orbit around other stars. This is really important because the structure of our solar system used to be our own benchmark for how our solar system might look. And that it turns out every one of those other solar systems, none of them look like our solar system. They look more like each other than they do like us. So it starts you thinking. Is there something unique about our configuration? Maybe we finally found something that tells us we're special in this galaxy, when all the other discoveries said we were not. These are important questions. It's a whole new branch of our field. I don't have a good word for it yet, but comparative solar systemology. All right? Where you get to see how we fit into that. To understand, maybe we know in those other solar systems there are no terrestrial planets like Mercury, Venus, and Earth. There are none nearby the host star. They got flung out of their solar systems. This, you know, it makes you look over your shoulder in the evolution of our own solar system. And there's evidence to suggest that, in fact, we may have had 2 or 3 times as many planets as we now do in the earliest phases of the solar system. What I love to think about is whether those planets had oceans and they have undersea vents that melt the ice, and here they are flung out into the galaxy without a host star.
Don't need it.
Somehow sustaining an ecosystem without a care in the world about the rest of the galaxy. Because the heat from this undersea vents are sustains their life.
Well, with that vast thought, Mr. President, I think you have the job of trying to wrap this up.
Well, I already know what to say. You know what? If they're all out there, I hope they have the best of what we have and fewer headaches. Let me say, Hilly and I have enjoyed every one of these, but this has been very, very special. I think our guests were both terrific, and all of you who asked questions. Albert Einstein once said the important thing is to not stop questioning, which is just what they said. So you don't have to stop questioning, but you do have to stop doing it right here because we're out of time. And I'd like to invite all of you to join us in the State Dining Room for a reception in honor of our guests and all the students and everyone else who's here. Let's go in there and you can continue your questions. Thank you very much.